What's up, guys? So today, let's talking about applications of the Fourier transformation of Boolean function. This is an interesting topic. So, one idea that I want to I want to describe is a linear bound. So, I should say linear programming bounds. This is an interesting topic, and the proof is also interesting. So I want to spend some time to discuss linear programming bounds of the binary linear code. Binary linear code. Okay, so let me just quickly remind you. What is the standard definition, right? So let's say f, which you take f is a Boolean function, which from 0, 1 to n, this is a Hamming space that I previously introduced, and and we can define a Fourier coefficient f. Let's say f of a coefficient, let's say y, which is inner product of f of x and the chi of y of x, which is a summation of x belongs to the Hamming space, and f of x minus 1 summation of xi, yi from 1 to n. Okay, and get 1 over 2 to the n, and you do the following. Okay, and yeah, so by this is you previously I proved this where forms are also normal basis, so you can easily write f of x to be what? To be a summation of f hat of y and a character of chi of yx. Okay, chi of y is defined by this. Okay, by sum over sum. This is inner product, and then with all the y. Okay. Y is also in the Hamming space. Okay, and let me just recall that the standard f and g inner products 1 over 2 to the n, f of x, g of x, you take x to be all the Hamming space. Okay, so this is the standard. Just write down. So chi of y of x is defined to be minus 1 summation of xi, yi, I from 1 to n. Okay, so this is the standard. Just a one page summary of the Boolean Fourier transformation of the Boolean function. Okay, we can use this to compute something which is really weird. Okay, so the idea is that let's start with some code. So if you don't know code means, you can view it's just a k-linear, I should say a k-dimensional subspace of the Boolean function of the Hamming space. Okay, so you take chi to be some linear code with the binary Hamming space, and you can define C to be the dual code. Okay, so dual code is just dual space. If you just dual space. Okay, so one can define AI to be a so-called weight distribution, and this is hard to understand. So what I'm saying is that the AI is defined to be the x belongs to the code such that the Hamming weight is W. Okay, so sorry, it's I. I, right? So this means that your x has a I is 1. Okay. Okay, and the number of it. Okay, and also you can define AI dual to be the same thing. So x belongs to C dual. X has the weight I. Okay, so obviously we have what? We have the number of the vector in the code is just summation all the weights, right? Because the weights is basically because I already defined AI to be a number, so I don't need this. So the weight will be n can be I from 0 to n. Okay, because you have n bit string, right? So either n of it's 1 or right, and we know that a0 is 0. Okay, because which is I only got one string for 0, 0, 0, 0. Okay, so this is weird. How do I find the connection between the C and in terms of these kind of things? Okay, so this is the weird thing that the one can compute. Okay, so Okay, let me just write lemma. Okay, so this is a weird result. First result that AI is 1 over CDO summation of AK this and the KIK of this. Okay, and K from 0 to N. And where is KIK? This is a strange polynomial that I will say later. So L from 0 to K, minus 1 to L, K to L, minus KI minus L. Okay. Okay, so this is the proof that I will give in this lecture. I will give in this video. Okay, so let's quickly let's go to the proof. Okay. Also, the proof is very interesting. Okay, so proof is that we first try to compute the characteristic of the Fourier transformation of the characteristic with the weight W. Okay, so this means that this function x means that if x is weight W, then I give you 1, else is 0. Okay, so I want to compute the Fourier transformation. Right? So let's take kind of x to be minus x dot with y, and the summation x belongs to chi. Okay, so this is a Fourier transformation. Okay, so this is a Fourier transformation of 1 of chi with chi yx. Okay, so this is a interesting object that one can try to compute. Okay, so what is this? Okay, so you need to take this, right? Okay, so this is maybe the difficult part, right? So this is what you need to compute. So you need to, so basically what you are doing is that you take 1 over 2 to n and then you sum all the x, right? But with the weights w and the minus 1 x dot with y. Okay, so this is just 1 over 2 to n summation x with w and the minus 1 summation xi yi. Okay, now you can see that this is summation of xi y, right? But x with weight w, so you can actually separate, right? You can just separate into different parts. Okay. Okay, so that means what? That means that okay, so let me just explain the detail. We need to do summation of this, right? But actually, this is that you can separate it into different parts, right? So you can separate into like this. And the minus 1, you do a summation, and then with, let me just okay, so this is the technical part that we need to spend some time and try to understand what the hell is going on. Okay, so this is sum over all the weights with W, right? So let's do this. Okay, so let's preserve. Let's try to write. Let's try to see that. Okay. Let's see. How should I explain this? How should I write this? Okay. So let's write this. Okay, so let's write. Let's see. This is your y, right? And so let's say this is. So this is minus 1. Only depends on what is the y hit with the x, right? So you fix some x with weight w, right? So you have w1 here. You can choose a w with 1, and there's a y there. Y may have some number which 1, some number 0. Okay, but let's take L. Let's take L to be the. Let's take L to be the number of ones. Which hit with this. Okay, let me just try to see this. Okay, how about like, okay, then let me just let's write y to be. Let's write all the 1 here and all the 0 here. Let's arrange this, right? Because I can. This is a range. Well, I can fix y to be this, and then when I choose x to be w, right? And this is all. Then I can take L part, which is here. and then this part. So this is the part that this is the number of intersection ones. Okay, so let me just write down. L is a number of intersection. 1 with X and Y. Okay, so I just count how many position that X and Y are both V1. Okay, that's the number of its L. Okay, so now it's easy, right? Because L is either from 0 to the Y. Because because at most there is so many Y, right? Okay, and the result will be minus L, right? Because if the intersection is 1, then I get minus 1. If it's even, like if it's odd, then I get minus 1. If it's even, I get the positive. I get 1, and the Y I choose L. Okay, because I can choose for each Y I choose a fixed L, and the rest minus Y is the rest 0, right? So I can omega minus L. Okay, this is a number of 1. This is the number of zeros that I can put. Okay, okay, this is interesting, and yeah, this is the first part. Okay, the second part is that let's do the Fourier transformation of the code. Okay, so this is simple. You just count this. Okay, you take xn and 1 to the c of x times an exponential, not exponential, minus x dot y, and this is sum over all of x. Let me just clear this. So let me just sum over x, right? So I'm sum over x, which is I only count a characteristic. So I get 1 over 2 to n. X belongs to the code minus xy. Okay, so this is a very simple observation that this is non-zero. This is non-zero when y belongs to the dual code, because when y belongs to the dual code, that these terms will orthogonal, right? So it's so it will give you 1. Right? So sorry, it's gonna give you 1, right? Because all x dot with this y will be 0. Okay, otherwise it's 0. Else is 0. Okay, so this is easy to prove. Okay, so you can check. Okay, so amazingly, this one of your y is actually the it's 1 for this term, right? So this is the this result should be the dual code, number of dual code divided by 2 to n. Okay. Okay, and sorry, I'm stupid. This is 1 over 2 to n. And for when you sum x, all these terms only survive when y belongs to the dual code. Okay, when y belongs to the dual code, there are how many terms of it? It's c, right? So you get the c times the identity with the dual code. Okay, so now we can use a Parseval. Right? We get a Parseval theorem, which is what I said previous, that Parseval theorem says that the inner product of f and g can be written as the Fourier coefficient. So basically, you can do the Fourier coefficient of y, and the g have y, and then you sum over y. Okay, so I can use a Parseval theorem on these two functions. The first is the weight distribution. The second is the code distribution. Okay, so let's do this. This is easy to, this is by definition, right? Because you do the, which is by definition is 1 over 2n with the weight distribution. And for the rest part, you get sum over y belongs to x of n, where one of the Fourier coefficient of c of y and 1 over the Fourier coefficient of w. Okay, and then you see that this is just this. And this is just this. This weird guy. Okay, but before this is KIK, right? So let's give a name. Right? This is KIK. Okay, so you can combine this, you get the, let's see. So for this one, you get c divided by 2 to the n, 1 over c dual y. And then for this one, you get the k omega y. Okay, there's another 2 to n. Okay, so remember this is what we derived. Okay, so 2 to n can cancel each other. Let's say 2 to n can cancel with each other. So you get cancel 1. So finally you get a omega is 1 over c. So weight distribution of omega, basically the number of the omega weights give you very strange for the transformation, which is kwi. Oh my god. Okay, so this is the proof. Okay, and this polynomial has a weird name. Has a strange name that I guess it's from the I guess it's from the Russian. Okay, so let me just copy his name. Let me just find it. Okay, so this is called yeah, I just find it. Yeah, because I somehow like easy to forget its name. Okay, Kravchuk polynomial. Okay, let me just write down. So it's Kravchuk polynomial. Okay, for our previous definition that is defined to be right. So ki of x is defined to be what? Oh, bad notation. Okay, let me just it's this. Okay, so let me just try to copy this. Okay, maybe I cannot copy this. Let me just okay, so I mean it's fine. Okay, yeah. So this is just this polynomial. Okay, let me just try it down. So it's a summation. Let's say j from 0 to I. Okay, maybe I use W. Yeah, notation is better. Okay, so j from W, and I take the minus j, as I said it. So x choose j minus. So you need to fix n. Right? So n is a fixed variable that you need to choose, and k minus j, W minus j. Okay. Okay, so simple example. Let's say if chi 0x, right? So for fixed n, that you can add n here. Will be when you put j equals to when you put w equals 0, you only get one term, right? This is right. You can get one term because j can at most be 0, right? So you get the first term is 1. Or k1 xn, you get 2 terms. Okay, the first term is n, right? Because this is w choose 1. Choose w to be 1, right? So j equals to equals 0, you get n choose 1, and then which is positive, and another term is minus 2x because come from here. Okay, then k0 xn will be 2x squared minus 2nx plus n choose 2. You just plug in and you get something like this. Okay. Okay, so this is what we got. Okay, and this cross-code is not cross-code. Kravchuk polynomial is also normal. Okay, so I will prove the also normality of the Kravchuk polynomial in the next videos. Okay, but let me just quickly derive the linear programming bounds. Okay, so the result is what? The result is the following. Right? The result is this AK. This will be summation of this. Okay, so you can see that this is original or derived, right? So but I can exchange C with C dual. So this will be AW of dual, and this will be AI, but no dual. But this is Kravchuk polynomial. Okay, so you will get the following like this. Sorry, this is dual. Okay. The reason is the following, because C divided by 2 is 1 over C dual. Okay, this proof is very simple. You can prove it by Lagrange theorem. Okay, if you know the group theory, then this should be easy to prove. Okay, so I from 0 to n. Okay, a to I. Okay, so let's say so for k from 0, 1 to up to n. Okay, then you can get one kind of inequality, right? So this is there's a name called this inequality. This inequality just tell me that for any code C, that the least guy is positive, right? Because by definition, this AK dual is positive. Okay, so this gives you a very strange result, right? Basically tell you that weight of the code distribution times with this Kravchuk polynomial is positive. Okay, so k from 0, 1 to up to n. Okay, so remember the AI is the number of the x belongs to the code with the weight w, or with the weight I. Let me just choose w. Okay, so now we got what? This is the linear programming. Okay, so you can write down linear programming problem, so theorem, which is a linear programming bound, which is what we derive using the technique of the Fourier analysis. Okay, so let's say you take any, so it's like for any code, C belongs to xn. Let's say the distance is d with distance d. So distance d means that AI is 0 for, right? Because so AI a0 is 1. But no more, the smallest distance must be d. Okay, so it means a1, a2 up to ad minus 1 is all 0. Okay, and what you're going to do is the C, right? So C is now this is bounds, right? Because the C is a summation of all the I from 0 to n, and by this condition that we get C is less or equal to, because we don't know whether this is necessary, sufficient, right? We don't know if this is necessary, so it's 1 plus the solution. So this solution is all, it must satisfy this of the following. You need to maximize this, because you want to find the upper bound, right? So you can try to maximize this. So you need to maximize all the AI sum from I to n. Okay. But basically you know it's 0. Okay. And then sum from AI, KI, KKI, I from D to N. Because this is what the distance means, and the greater equal to the first term. Greater equal to the first term, right? So first term is when k equals 0, right? So k0i, they can prove is n. Okay, so let's do this. So k0i is when x puts I. You can see this is let's see. Not this. Yeah, so we need k0. Okay, so say k0 is, and choose k. Okay, greater equal to this. Because our bound is that this should be positive, right? So this is for every k from 1 to 2 to n. Okay, so this is a linear programming bounds, because the code of C is bounded by this Kravchuk polynomial. Okay, this is the thing I want to say here. Okay, so now so we derive this linear programming bounds by using this Fourier transformation and Kravchuk. In the next video, that I will prove the orthogonality of Kravchuk, and I will say more about this strange. I will say more about this the usage of this Fourier transformation of Boolean function. Okay, hopefully you like this video. See you.